July 24, 1943, somewhere south of Truk Lagoon in the Central Pacific, Lieutenant Commander Lawrence Daspit stood at the periscope of USS Tinosa, watching the 19,250-ton Japanese whale factory ship Tonan Maru Number Three sitting motionless on the flat ocean surface, dead in the water, alone, unescorted. The kind of target submarine commanders dreamed about, the kind that could end a war patrol in glory and send a critical enemy asset to the bottom. Daspit had already fired 4 Mark 14 torpedoes from 4,000 yards. 2 had struck the massive hull squarely, the dull thuds audible through Tinosa's pressure hull. The ship should have been sinking. Instead, it wallowed on the surface, damaged but refusing to die. He fired 2 more torpedoes. Both hit. 6 torpedo impacts against a stationary merchantman, and still the target remained afloat. What happened next would force the United States Navy to confront a truth it had spent nearly 2 years denying. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. A truth that had cost thousands of American lives, dozens of irreplaceable warships sunk by Japanese forces that should have been destroyed, and strategic opportunities squandered because the primary weapon of the American submarine force was fundamentally, catastrophically defective. Daspit maneuvered Tinosa into perfect position, 875 yards directly abeam of the target. He could not miss from this range. The geometry was flawless, the sea calm, visibility excellent. He fired 9 more torpedoes, 1 at a time, observing each carefully through the periscope as it ran true and straight toward the helpless ship. 9 torpedoes struck the hull at 90-degree angles, the optimal impact for maximum damage. Daspit heard each impact as a metallic clang transmitted through the water. Not one exploded. 15 torpedoes fired under ideal conditions at a stationary target. 15 hits. 0 explosions. Daspit, suspecting he had received a defective production batch, kept his last torpedo unfired for technical analysis and withdrew before Japanese aircraft could respond to the freighter's distress calls. His patrol report, meticulous and damning, documented in excruciating detail the most comprehensive combat test of American torpedo reliability ever conducted. The evidence was irrefutable. The Mark 14 torpedo, the most expensive and supposedly sophisticated weapon in the American arsenal, was a catastrophic failure. The roots of this disaster reached back more than a decade, to the depths of the Great Depression, when budgetary constraints and institutional arrogance combined to produce a weapon that had never been properly tested and would fail American submariners when they needed it most. The story of how American engineers finally fixed these problems reveals not just technical ingenuity, but a bitter bureaucratic battle between submarine commanders dying in combat and ordnance officers defending their reputations in Washington. The Mark 14 torpedo entered design in January 1931, intended to arm the new fleet submarines then under construction. The specifications were ambitious for the era: 20 feet 6 inches long, weighing 3,000 pounds, carrying a 643-pound Torpex warhead, achieving 46 knots at a range of 4,500 yards. Most significantly, it would incorporate the Mark 6 exploder, a magnetic influence device designed to detonate beneath enemy ships' keels, breaking their backs and ensuring kills without requiring direct hull contact. The Mark 6 represented cutting-edge naval technology. Rather than demanding a direct hit, it would detect changes in Earth's magnetic field caused by a ship's steel hull passing overhead, firing when these magnetic variations reached predetermined levels. German U-boats had experimented with magnetic exploders in World War I with limited success. British torpedoes used them with moderate results. The American Mark 6 was engineered to be more sensitive, more reliable, more sophisticated than any previous design. The fatal flaw was testing. Each Mark 14 cost over $10,000 in 1931 currency, equivalent to roughly $200,000 today. In the Great Depression, with naval budgets slashed and Congress scrutinizing every expenditure, the Navy was extraordinarily reluctant to destroy expensive torpedoes in live fire tests. Instead, The Mark 14 underwent testing with exercise heads, dummy warheads filled with water to approximate combat weight, then recovered after firing for reuse. This protocol seemed economical and sensible. It was completely inadequate. The exercise head, while matching overall torpedo weight, had fundamentally different weight distribution than the combat warhead. The live warhead concentrated 643 pounds of high explosive in the torpedo's forward section. The exercise head distributed water throughout the warhead space. This difference affected trim and hydrodynamic characteristics in ways invisible during testing, but devastating in combat. Furthermore, no live fire tests were conducted against actual target ships to verify the exploder would function under combat conditions. The Mark 6 magnetic exploder was classified so secret that submarine commanders weren't allowed to examine it or understand its operation. The entire system entered combat service based on mathematical calculations, laboratory tests, and exercise firings that never replicated actual battle conditions. The weapon America's submarine force would carry into the largest naval war in history had never been truly tested. 7 days after Pearl Harbor, the first signs of catastrophic failure appeared. December 14, 1941, USS Seawolf, commanded by Lieutenant Commander Frederick Warder, encountered a Japanese freighter anchored off the southern coast of Mindanao in the Philippines. Warder maneuvered into perfect attack position, range 3,000 yards, target stationary and unescorted. He fired 8 Mark 14 torpedoes, 7 missed entirely, passing beneath the target or running wild. The 8th struck the freighter squarely amidships. Seawolf's crew heard the dull metallic clang through their hull. No explosion followed. The torpedo, packed with 643 pounds of Torpex explosive, had hit directly and failed to detonate. The freighter, alerted but undamaged, got underway and escaped. The pattern repeated with numbing regularity throughout December and into early 1942. USS Sargo, commanded by Commander Tyrrell Jacobs, encountered 4 Japanese cargo ships off Indochina on Christmas Eve, steaming unescorted. Jacobs fired 3 torpedoes at each of 4 targets, 12 torpedoes from ranges between 1,000 and 2,000 yards under perfect conditions. Every torpedo either missed entirely or malfunctioned. Not a single explosion. Jacobs observed through his periscope as torpedo after torpedo passed beneath targets or struck without exploding. He fired his final 4 torpedoes at a large cargo ship that had stopped to investigate. All 4 ran beneath the stationary target. Sargo returned to Manila Bay on December 30th with her crew demoralized, having expended all 24 torpedoes without sinking a single ship. Commander Jacobs filed a report stating unequivocally that torpedoes were running far deeper than set depths, passing harmlessly beneath targets. The Bureau of Ordnance in Washington, responsible for torpedo development and production, dismissed his complaints with barely concealed contempt. The problem, Bureau officers insisted, was submarine commanders who didn't understand proper torpedo maintenance, crews who weren't performing correct pre-launch procedures, captains who couldn't execute proper attack approaches. The Bureau's position was that the Mark 14 was thoroughly tested, and any failures were operator error. This position would be maintained with bureaucratic obstinacy for nearly 2 years, while American submarines fired thousands of defective torpedoes and Japanese merchant ships steamed safely to port. The submarine commanders kept filing reports. The statistics told an undeniable story. In 1942, American submarines in the Pacific fired 1,442 torpedoes at Japanese targets. They claimed to have sunk 211 ships, totaling nearly 1.3 million tons. Post-war analysis of Japanese records conducted by the Joint Army-Navy Assessment Committee revealed the true figures: 109 ships totaling 418,701 tons, barely 30% of claimed tonnage. The Mark 14 had 3 separate catastrophic defects, each masking the others and making diagnosis extraordinarily difficult. The first defect was depth control. The torpedo ran 10 to 11 feet deeper than its set depth because the depth control mechanism had never been properly tested with the heavier combat warhead. When engineers increased warhead weight by 80 pounds during final development to increase lethality, they failed to recalibrate the hydrostatic depth sensor. Additionally, this sensor was positioned on the torpedo's body, where water flow created pressure variations that confused the mechanism. As the torpedo accelerated to combat speed, water flowing over the hull created a pressure drop at the sensor location through Bernoulli's principle, the same effect that creates lift on aircraft wings. The depth mechanism, detecting this pressure drop, interpreted it as the torpedo being too shallow and responded by trimming deeper. The faster the torpedo ran, the greater this effect became. Every Mark 14 fired in combat in 1941 and 1942 ran far beneath its intended depth, passing harmlessly under targets. The second defect was the magnetic exploder. The Mark 6 was designed to detonate when detecting the magnetic signature of a ship's steel hull overhead. In theory, brilliant. The torpedo would run beneath the target and explode under the keel, where shock waves and gas bubbles would be most effective. In practice, wildly unreliable. Earth's magnetic field varies significantly with location, affected by latitude, local geology, and other factors. The Mark 6 had been tested near the Naval Torpedo Station in Newport, Rhode Island, where magnetic field characteristics were suitable for its operation. In combat across the Pacific, operating near Java, the Philippines, Guadalcanal, and Japan, magnetic field characteristics were entirely different. The Mark 6, calibrated for Newport, failed catastrophically in the combat environment. Some torpedoes exploded prematurely, detonating 50 or 100 yards before reaching targets when the magnetic trigger detected signatures at excessive range. These premature detonations caused minimal damage, merely alerting targets and allowing evasive action. Other torpedoes passed beneath targets and failed to explode because magnetic field changes weren't sufficient to trigger the exploder in actual operating environments. The deep running defect and magnetic exploder defect masked each other. Torpedoes running too deep wouldn't trigger the magnetic exploder because they passed too far beneath targets' magnetic signatures. If depth control could be fixed, presumably the exploder would work properly. But even after depth was corrected in mid-1942, the magnetic exploder continued malfunctioning, revealing the third catastrophic defect in the contact exploder mechanism. The Mark 6 incorporated both magnetic and contact firing systems. If the magnetic system failed to detonate as the torpedo passed beneath the target, the contact exploder would theoretically fire when striking the hull. This contact system used a firing pin design that had worked reliably in older torpedoes running at slower speeds. The Mark 10, which the Mark 14 replaced, achieved 36 knots. The Mark 6 contact exploder had been designed and tested for that speed regime. The Mark 14 ran at 46 knots, 28% faster, and nobody had tested whether the contact exploder would function at higher impact velocity. When a torpedo traveling at 46 knots strikes steel hull, deceleration is nearly instantaneous and extraordinarily violent. The firing pin in the Mark 6 contact exploder was relatively heavy, held in place by a spring that had to be stiff enough to prevent premature firing during normal handling, but weak enough to allow the pin to move when striking targets. At the Mark 14's high impact velocity, particularly when striking at 90-degree angles as submarine commanders were trained to shoot, sudden deceleration caused the firing pin to bind in its housing before striking the detonator cap. Friction forces on the pin during deceleration exceeded spring force, driving it forward. The result was that perfect shots, direct 90-degree angle hits exactly as taught in submarine school, were most likely to be duds. Only oblique angle hits, where deceleration was more gradual, allowed the firing pin to function properly. This defect had actually been discovered and corrected in older torpedo models in 1922. The solution had been using stiffer springs and lighter firing pin components. But when the Mark 6 was designed, incorporating the new magnetic exploder function, the earlier lesson was forgotten. The contact exploder inherited the old firing pin mechanism without testing to verify it would work at the Mark 14's higher speed. Japanese merchant ships began arriving in port with American torpedo dents, and sometimes with unexploded American torpedoes lodged in their hulls. The ultimate humiliation for submarine crews who had executed perfect attacks. The cost in American lives and lost opportunities during 1942 and early 1943 was staggering. Lieutenant Commander Eugene McKinney, commanding USS Tambor, fired 8 torpedoes at a Japanese destroyer in April 1942 from 800 yards. He heard 8 dull metallic clangs as they struck the destroyer's thin hull plating. None exploded. The destroyer, now fully aware of Tambor's position, counterattacked with depth charges that shattered light bulbs throughout the submarine and caused leaks in multiple systems. Tambor barely escaped. The morale impact on submarine crews was severe. Men who had trained for years, who took their boats into harm's way despite submarines having the highest casualty rate of any American combat arm, who risked their lives executing perfect attacks, saw those attacks fail because their primary weapon was fundamentally defective. The breaking point came in stages throughout 1943 as the evidence became too overwhelming to deny. The depth control problem was addressed first, though only after months of bureaucratic resistance. In June 1942, Rear Admiral Charles Lockwood, then Commander Submarines Southwest Pacific, conducted systematic tests, firing torpedoes through nets at known depths. The tests proved conclusively that torpedoes were running approximately 10 feet deeper than set depths. Lockwood reported his findings to the Bureau of Ordnance, which initially refused to accept them. Only after repeated tests and mounting combat failures did the Bureau grudgingly acknowledge the depth problem. The fix was relatively simple once the problem was identified. Relocating the depth sensor to the torpedo's mid-body, where hydrodynamic effects were minimized, and recalibrating the mechanism for actual combat conditions. By late 1942, the depth control issue was largely resolved, but the performance didn't improve as expected because the magnetic exploder continued failing. The magnetic exploder problem proved more difficult to fix and more difficult for the Bureau of Ordnance to accept. Submarine commanders reported premature detonations with increasing frequency, torpedoes exploding far short of targets, visible through periscopes as underwater detonations that caused no damage. The Bureau insisted the problem was improper maintenance or incorrect calibration procedures. Resources were devoted to training submarine torpedo crews on proper magnetic exploder adjustment, rather than questioning whether the device itself was fundamentally flawed. The turning point came in May 1943 when Lieutenant Commander Dudley Morton, the most famous and successful submarine commander in the Pacific Fleet, returned from a patrol having achieved no sinkings despite perfect attack opportunities. Morton, commanding USS Wahoo, was a legend in the submarine force. His previous patrols had been spectacularly successful. His failure convinced Rear Admiral Lockwood, by then Commander Submarine Force Pacific, that the magnetic exploder had to be deactivated. Even then, Lockwood hesitated. He waited to see if Bureau of Ordnance Admiral William Blandy might find a solution. The Bureau sent an expert to investigate, who found nothing wrong with maintenance procedures, but submitted a report blaming submarine crews anyway. Finally, on June 24, 1943, Lockwood ordered the magnetic exploder deactivated fleet-wide. Submarines would rely solely on contact detonation. This decision was made 20 months into the war, 20 months during which thousands of torpedoes had been fired with magnetic exploders that failed to work in combat conditions. The order should have solved the problem. It didn't. With magnetic exploders deactivated, the contact exploder's catastrophic defect became impossible to ignore. This is where Lieutenant Commander Daspit's experience with Tinosa became decisive. Daspit's July 24 encounter with Tonan Maru Number Three represented a controlled experiment conducted under combat conditions. 15 torpedoes fired at a stationary target under ideal conditions. 15 hits, 0 explosions. The last torpedo, kept unfired for analysis, provided physical evidence that could be examined by experts. Daspit's patrol report was meticulous, detailed, and irrefutable. Rear Admiral Lockwood recognized that Daspit's experience was proof the contact exploder was defective. Lockwood was himself an experienced submariner, having commanded submarines in the 1920s and 30s before moving to senior positions. He had listened to 2 years of his commanders reporting torpedo failures. He had watched the Bureau of Ordnance blame every failure on operator error. He had seen the morale impact on crews risking their lives with defective weapons. He now had documented proof that the contact exploder was fundamentally flawed. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Lockwood ordered immediate testing. His staff constructed a testing range where dummy warheads could be dropped from a pier crane onto steel plates, positioned at various angles to simulate torpedo impacts. The tests revealed that the firing pin mechanism bound and jammed at high impact velocities, particularly at 90-degree impact angles. The heavier the firing pin and the stiffer the deceleration, the more likely binding became. Direct 90-degree hits, the supposedly perfect shots that submarine commanders were trained to take, generated such sudden deceleration that the firing pin couldn't move fast enough to strike the detonator cap. The contact exploder was fundamentally defective, and the defect became worse with perfect shooting. The solution came from an unexpected source. During the Pearl Harbor attack on December 7, 1941, American anti-aircraft fire had shot down several Japanese aircraft. Engineers examining wreckage at the Naval Air Station discovered that propeller blades were made from lightweight aluminum alloy rather than steel used in American propellers. This material, strong enough for its purpose but significantly lighter than steel, suggested a solution to the firing pin problem. If the firing pin were made from lightweight aluminum instead of steel, it would have less inertia during deceleration and would be less likely to bind. Tests confirmed the theory. Aluminum firing pins with properly calculated spring rates functioned reliably at all impact angles and velocities. By September 1943, 21 months after Pearl Harbor, modified torpedoes with aluminum firing pins and other design improvements began reaching submarines at Pearl Harbor and Fremantle. The transformation in American submarine effectiveness after September 1943 represented one of the most dramatic capability shifts in naval warfare history. From December 1941 through August 1943, American submarines had operated with their primary weapon barely functional. 3 separate catastrophic defects, each masking the others, had rendered the Mark 14 unreliable at best and completely useless at worst. After September 1943, with all 3 defects corrected, the Mark 14 became the weapon it had been designed to be. Depth control now worked properly. The magnetic exploder had been permanently deactivated in favor of contact detonation only. The contact exploder now functioned reliably at all impact angles and velocities. Submarine commanders who had learned their trade despite defective weapons now possessed torpedoes that actually worked. The effect on Japanese shipping was immediate and catastrophic. In 1942, American submarines fired 1,442 torpedoes and actually sank 109 ships for 418,701 tons. In 1943, as torpedo problems were gradually corrected, submarines fired 3,937 torpedoes and sank 284 ships for 1,349,473 tons. In 1944, with fully functional torpedoes, submarines fired 6,920 torpedoes and sank 492 ships for 2,388,000 tons. The effectiveness improvement was roughly tenfold once torpedoes began functioning properly. By war's end, American submarines had sunk 1,178 Japanese merchant vessels totaling 5,503,491 tons, representing 54.6% of all Japanese shipping losses from all causes. USS Flasher, commanded by Commander Reuben Whittaker, intercepted a convoy off Indochina on December 22, 1944. Whittaker fired 6 torpedoes at 3 tankers. All 6 functioned perfectly. 3 tankers, the 10,000-ton Tonan Maru, the 9,200-ton Arita Maru, and the 9,200-ton Otowasan Maru, carrying critical fuel oil from the Dutch East Indies to Japan, went to the bottom in less than 20 minutes. In a single attack, Whitaker had sunk over 28,000 tons of shipping and sent hundreds of thousands of gallons of irreplaceable fuel to the ocean floor. USS Barb, commanded by Commander Eugene Fluckey, achieved even more spectacular results. On her 11th war patrol in 1945, Barb sank 17 ships totaling over 96,000 tons, setting a record for tonnage sunk on a single patrol that would never be exceeded. These were not lucky hits or random successes. These were precisely executed attacks using weapons that now worked as designed, delivered by submarine commanders who had learned through bitter experience exactly how to employ them to maximum effect. The toll on Japan's economy was catastrophic. Japan was an island nation utterly dependent on seaborne logistics. Raw materials from conquered territories in Southeast Asia, China, and the Dutch East Indies had to be shipped to Japan for processing. Finished military equipment had to be shipped from Japan to forward bases. Food imports were essential to feed the population. Oil from the Dutch East Indies was critical to every aspect of the war economy. By January 1945, the Japanese merchant fleet had been reduced to barely a quarter of its December 1941 strength. Tankers carrying oil were being sunk faster than they could complete round trips. Cargo ships bringing raw materials were going to the bottom with their holds full. Food imports had declined to the point that rationing in Japan approached starvation levels. The industrial consequences rippled through every aspect of Japan's war effort. Oil refineries shut down for lack of crude. Steel mills closed for lack of iron ore and coking coal. Aircraft factories stopped producing for lack of aluminum. Training programs for pilots and sailors ground to a halt for lack of fuel. Naval vessels sat pierside or swung at anchor, immobilized by lack of oil. The combined fleet, once the third largest navy in the world, was reduced to immobility. American strategic bombing, which received enormous attention in popular accounts, was actually secondary to the submarine blockade in destroying Japan's ability to wage war. Factories couldn't operate without steel, aluminum, coal, and oil, regardless of whether they were being bombed. The submarine campaign had strangled Japan's economy before the atomic bombs provided a face-saving reason to surrender. The story of the Mark XIV represents one of the most costly bureaucratic failures in American military history. The weapon had been inadequately tested before the war due to budget constraints and institutional arrogance. When combat revealed catastrophic defects, the Bureau of Ordnance spent nearly 2 years denying problems existed and blaming submarine commanders rather than fixing the weapon. This institutional failure cost American lives, allowed Japanese forces to operate longer than necessary, and prolonged the war. The submarine commanders who fought through those first 2 years with defective torpedoes demonstrated extraordinary courage and perseverance. They executed perfect attacks, knowing their weapons would likely fail. They filed detailed reports documenting failures, knowing the Bureau of Ordnance would dismiss their observations. They kept fighting despite seeing their shipmates die in boats that were hunted and sunk while their own torpedoes refused to work. The engineers who finally fixed the Mark XIV, working under Rear Admiral Lockwood's direction at Pearl Harbor, demonstrated the scientific method and engineering rigor that should have been applied before the war. They conducted systematic tests to isolate each defect. They developed solutions based on evidence rather than theory. They implemented fixes quickly once problems were identified. They proved that when institutional barriers were removed and engineers could focus on solving problems rather than defending reputations, American technical capability was formidable. The lesson extends beyond torpedo development to broader questions about institutional accountability, the importance of realistic testing, and the dangers of bureaucratic inertia during wartime. The Bureau of Ordnance's refusal to acknowledge torpedo defects for nearly 2 years represents a failure of leadership that should have resulted in courts-martial. Instead, the officers responsible for the Mark XIV's inadequate testing and the subsequent cover-up faced no meaningful consequences. The submarine commanders and crews paid the price for institutional failure. They fought with defective weapons for 21 months, while the Bureau of Ordnance defended its reputation rather than fixing the torpedo. When the Mark XIV finally worked as designed, American submarines proved decisively that they could have been strangling Japan's economy from the war's first weeks if given functional weapons. The transformation from catastrophic failure to devastating effectiveness took just weeks once all defects were corrected. The weapon that had been the submarine force's greatest frustration became its most effective tool. The torpedo that Japanese merchant captains had learned to fear only after September 1943 could have been terrorizing them from December 1941 if proper testing had occurred before the war. By war's end, the Mark 14 had sunk more enemy tonnage than any other American weapon system. It remained in service for nearly 40 years in the United States Navy and even longer with other navies. The post-war Mark 14 incorporated lessons learned from fixing the wartime defects, becoming a genuinely reliable weapon that performed as its original designers had intended. The story serves as a case study in what happens when institutional pride takes precedence over combat effectiveness, when budget constraints lead to inadequate testing of critical weapons, and when feedback from combat forces is dismissed rather than investigated. It also demonstrates what American engineering and industrial capacity could achieve when institutional barriers were removed and talented people focused on solving problems rather than defending reputations. The submarine commanders who fought through 1942 and 1943 with defective torpedoes never received adequate recognition for their perseverance under impossible conditions. The engineers who fixed the Mark 14 worked in relative obscurity, their achievements known primarily within naval circles. But their collective effort, overcoming institutional resistance to deliver a weapon that finally worked, helped win the Pacific War by strangling Japan's economy and proving that technical problems, no matter how complex, could be solved when evidence was valued over bureaucratic pride. The human cost of the torpedo scandal extended far beyond simple statistics of ships not sunk or tonnage not destroyed. Every failed torpedo attack represented a moment when American submariners exposed themselves to deadly counterattack for nothing. Every dud that struck a target's hull and failed to explode alerted enemy escorts to the submarine's position, bringing depth charges that could crush a boat and kill everyone aboard. USS Growler, commanded by Lieutenant Commander Howard Gilmore, attacked a Japanese convoy in February 1943. Several torpedoes malfunctioned, and in the confusion of the failed attack, Growler was forced to surface directly in front of a Japanese gunboat. In the ramming and gunfire that followed, Gilmore was mortally wounded on the bridge. His last order, shouted down the hatch as he lay dying, was, "Take her down." The submarine dove, saving the crew but leaving Gilmore on the surface where he died. His Medal of Honor citation didn't mention that defective torpedoes had contributed to the tactical situation that cost his life. USS Wahoo, the boat that had made Lieutenant Commander Dudley Morton famous, was lost with all hands in October 1943 in the Sea of Japan. Morton had been one of the most aggressive and successful submarine commanders in the Pacific, but even his skill couldn't overcome the handicap of operating for 18 months with torpedoes that worked only intermittently. Whether better torpedoes earlier in the war would have allowed Wahoo to sink more targets and possibly avoid the situation that led to her loss remains unknowable, but the question haunted survivors who had served under Morton. The Bureau of Ordnance's institutional failure went beyond simple engineering mistakes. The Bureau had actively suppressed evidence of torpedo defects, blamed submarine commanders for reporting problems, and resisted corrective action even when presented with overwhelming proof. Admiral William Blandy, who headed the Bureau of Ordnance during much of this period, faced no professional consequences for the scandal. He retired as a 4-star admiral, his career untarnished by the torpedo failures that had cost American lives. The contrast with German torpedo development is instructive. The German Navy experienced similar magnetic exploder problems early in World War II during the Norway campaign in April 1940. German torpedoes suffered premature detonations and depth control issues remarkably similar to American problems. The difference was in institutional response. The German Navy immediately convened boards of inquiry, identified the problems within months, court-martialed the officer responsible for torpedo testing, and implemented fixes by late 1940. The German Navy's rapid response to torpedo problems stood in stark contrast to the American Bureau of Ordnance's 2-year denial and delay. German U-boats were operating with reliable torpedoes by late 1940. American submarines didn't achieve similar reliability until late 1943, 3 full years later. The institutional cultures that produced these different responses reflected broader differences in how the two navies handled technical failures and accountability. Japanese naval intelligence, monitoring American submarine radio traffic and interrogating crews from boats that were sunk or forced to surface, compiled detailed reports on American torpedo failures through 1942 and early 1943. These reports reached Imperial Naval General Headquarters in Tokyo and were analyzed by intelligence staff who drew precisely wrong conclusions from accurate observations. Japanese analysts concluded that American torpedoes were primitive weapons plagued by fundamental design flaws that reflected American technological inferiority. This assessment, based on real evidence of American failures, failed to understand that American engineering capability was formidable and that the failures were temporary problems American industry would eventually solve. Japanese anti-submarine doctrine, never strongly prioritized because intelligence insisted submarines weren't a serious threat, remained focused on protecting naval task forces rather than merchant convoys. This intelligence failure had strategic consequences. Japanese destroyer escorts and patrol craft, designed primarily for surface combat, lacked effective sonar, adequate depth charge equipment, and tactical doctrine for hunting submarines. Japanese naval construction priorities focused on battleships and fleet carriers for the decisive battle rather than unglamorous escort vessels for convoy protection. Resources that might have gone to building convoy escorts and developing anti-submarine warfare capability instead went to capital ships. By the time Japanese intelligence recognized that American submarines with functional torpedoes represented an existential threat to Japan's maritime logistics, it was too late to implement the convoy protection measures that might have preserved the merchant marine. The window for building adequate numbers of escort vessels and training anti-submarine warfare crews had closed. American submarines were already strangling Japan's economy, and no amount of belated countermeasures could reverse the cumulative losses. The post-war analysis, conducted by the United States Strategic Bombing Survey, concluded that the submarine campaign was more decisive in defeating Japan than strategic bombing. While B-29 raids received enormous publicity, and the atomic bombs ended the war dramatically, submarines had already destroyed Japan's ability to sustain industrial production by cutting off raw material imports. Factories couldn't produce weapons without steel, aluminum, and oil, regardless of whether they were being bombed. The survey's findings vindicated the submarine force and implicitly condemned the Bureau of Ordnance's failures. If American torpedoes had worked properly from December 1941, the economic strangulation of Japan would have occurred much earlier, potentially shortening the war by months and saving thousands of American lives lost in battles that might never have been necessary if Japan's logistics had collapsed sooner. The institutional lessons from the Mark 14 scandal influenced American weapons development in the Cold War era. The Navy established more rigorous testing protocols for new weapons systems, including mandatory live-fire tests against actual targets under realistic conditions. Budget constraints could no longer justify accepting weapons into service based on theoretical calculations and laboratory tests. The Mark 14's failures had proven too costly to risk repeating. Rear Admiral Charles Lockwood, who had fought the bureaucratic battle to fix the torpedo, became Commander Submarine Force Pacific in January 1943 and held that position through war's end. His willingness to challenge the Bureau of Ordnance and demand fixes, despite institutional resistance, made him a hero to submarine commanders. After the war, he wrote extensively about submarine operations, ensuring the story of the torpedo scandal became part of the historical record, rather than being buried in classified files. The submarine commanders who survived the war carried memories of attacking with defective torpedoes, watching perfect shots fail, and wondering whether their lost shipmates might have survived if weapons had worked properly. Lieutenant Commander Eugene Fluckey, whose boat Barb achieved spectacular success with functional torpedoes in 1944 and 45, later wrote that the greatest tragedy was not knowing how many more targets could have been destroyed in 1942 and 43 if torpedoes had worked from the beginning. The Mark 14, once corrected, proved to be a fundamentally sound design that remained in service far longer than most World War II-era weapons. The basic torpedo design, with improvements incorporating lessons learned from wartime experience, continued in American service until 1980. Foreign navies using American torpedoes kept Mark 14s operational even longer. The weapon's longevity validated the engineering principles behind its design once the testing and quality control failures were corrected. The story of the Mark 14 torpedo represents both the worst and best of American technical capability. The worst: inadequate peacetime testing, bureaucratic resistance to acknowledging problems, and institutional pride that delayed fixes while Americans died. The best: systematic problem-solving engineering rigor applied to identifying root causes and rapid implementation of solutions once institutional barriers were removed. The transformation from catastrophic failure to devastating effectiveness demonstrated that American engineering, when properly focused and supported, could solve even the most complex technical problems. For the submarine commanders who fought through those first 21 months with defective weapons, vindication came too late for many. 48 American submarines were lost during World War II, taking 3,505 men down with them. How many of those boats might have survived if their torpedoes had worked properly remains unknowable. But the question haunted the submarine force for decades after the war ended. The final accounting showed that American submarines, once equipped with functional torpedoes, achieved the most successful submarine campaign in naval warfare history. They sank more tonnage than German U-boats, despite operating for far fewer years and with far fewer boats. They proved that submarine warfare, executed with reliable weapons and aggressive tactics, could strangle an island nation's economy and fundamentally alter the strategic balance of a global conflict. The Mark 14 torpedo, initially a catastrophic failure that nearly crippled the American submarine force, ultimately became the weapon that won the Pacific War by economic strangulation. The journey from failure to success required courage from submarine commanders who kept fighting despite defective weapons, persistence from engineers who systematically identified and fixed each defect, and leadership from officers like Lockwood, who challenged institutional resistance and demanded accountability. Their collective achievement stands as testament to what American technical capability could accomplish when evidence was valued over bureaucratic pride and when solving problems took precedence over protecting reputations. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.